Hello dear students, today we'll discuss some more very important concept in the same oscillation chapter, that is phasor diagram. So until then what we have discussed, we'll glance over once again. So we have discussed the acceleration, that is of minus omega square x, where the particle executing the simple harmonic motion it is. And also we have already discussed the velocity, that is omega of root of a square minus x square. Velocity it is of a particle in simple harmonic motion it is. So now we are thinking of circular motion of a particle here. That means body executing the circular motion, does it says it is a oscillatory motion? No, it is not oscillatory motion, it is a periodic motion it is. So as we know, particle is moving from here and completing here. Means it is undergoing the repetitive to the original position of a fixed interval time it is. It is not said to be as an oscillatory motion, it is said to be as a periodic motion it is. That we have already discussed in the first class only. But the thing is, how it is related to the oscillatory if body is executing the circulatory motion. We never say that particle, when it is undergoes the uniform circular motion, it is purely periodic motion it is. It will not said to be as it is a simple harmonic motion it is. But when particle execute the circular motion, its projection execute the to and fro motion. That means it executes the oscillatory motion. So how it is? Now let us concentrate and let us discuss this part here. So uniform circular motion executing by the particle is not simple harmonic motion it is, or a oscillatory motion, but it is a periodic motion it is. Body executing the circular motion. But when particle undergoes the uniform circular motion, its projection executes the simple harmonic motion. What is simple harmonic motion? Which executes the to and fro motion. So this is a simple harmonic motion that we have already discussed. So s is equal to 0 at the mean position when it undergoes the extreme position of a positive direction and extreme position of a negative direction it is. So when it undergoes the to and fro motions, so look at here, particle is moving and coming to the mean position, next it will go to the negative extreme position, again it will come in. Means it is also look like a periodic motion, means after a certain time intervals it is trying to come back to its original position only. So this is the complete time period that also we have already discussed in the previous class while studying the time period of the particle executing the simple harmonic motion. One complete to and fro motion is called as a time period it is. So time required to complete the one oscillation. How many phases are there here? I mean to say that stages. So this is the first one, this is the second one. So when it is moving towards the mean position, so this is the first stage, second stage, third, right, and this is the fourth. So to understand this simple harmonic motion, 4 stages are there. So that means it undergoes one complete oscillation here. That also we have already discussed in the previous class, right? When particles undergoes the uniform circular motion, how we can say that its projection is going to be executing the simple harmonic motion. Once we have understood the simple harmonic motion thoroughly, so then we can understand through its projection form of when particle is under the uniform motion. So in your book also, I mean in the material also, or a textbook also, they had given the circular form of it, and they are showing some diagrams that particle executing the simple harmonic motion under the uniform circular motion it is. So how we are going to, let us cross check. So look at here, this is the circular form I'm going to draw, right? So this is nothing but the diameter, or else that it is x. As t is equal to 0 means the first part, it is particle starts moving from here, right, and moving, completing the circular form. It is, look at here, particle is moving from this point means that t is equal to 0. So once it is moving from certain part, say t is equal to t, it is at the point t is equal to t in the sense what here, certain time is taken to move from 0 time period to certain time. So this distance, right? So once you draw the projection here, means draw, so let us consider this part is what here, radius a. So radius of the circular form of the particle executing the uniform circular motion. So we are now saying the body executing the uniform motion is said to be as a simple harmonic motion. Never ever, because the body when executes the uniform circular motion is not a simple harmonic. It is a purely periodic motion of a particle. Then through this, how we can understand it is a simple harmonic motion is involved in it. That indicates what here, particles projection when it is executing the uniform circular motion behaves like a simple harmonic motion. That we are going to study detail here. See, look at here, this part I'll call it as it is a origin. From the origin, see, center point to any point on the circumference of the particle, this is r or what, radius. So here I'm taking radius as a here. That is nothing but when your particle is moving from to the next extreme position, what is this? Maximum amplitude, certain displacement, or the maximum displacement from the mean position to the extreme position. So that is what displacement, that is what the amplitude. So if you draw the line from the center portion of a circular path executing by the particle at the time period t is equal to 0 to t is equal to t. So direction also I have mentioned here. So then the angle is created here. What is this angle? This is called as a theta. Theta in the sense what here? Omega t. What is omega t? Because it executing the angular path. So angular displacement it is. So this part is what? Angular displacement with the time it is. So theta is equal to omega t here. Angular displacement. So theta is equal to omega t. Omega is what here? Angular frequency in time period t. So total angle is made from the t is equal to 0 to the certain time t is equal to t it is. So look at here. Once you draw the projection along the diameter of the circular path, the particle executing the uniform circular motion, but all this projection of a executing particle in a uniform motion is not said to be as a simple harmonic, as we have discussed in the previous classes. All oscillatory motions are not a simple harmonic motion. When it is said to be as a simple harmonic motion, it is no doubt all particles execute the oscillatory motion, execute the to and fro motion. When it is said to be as a simple harmonic motion, simplest harmonic form it is, where its force is equal to minus kx, where k is what is said to be as a m, k by m, or else omega by m it is. So we will discuss later one by one here. So it is said to be as a simple harmonic motion, force is equal to minus k raised to x. This should be proved, means it is the simplest form of harmonic motion it is. So simplest form of harmonic motion. So this should be proved. All oscillatory is a not simple harmonic motion. Then how we can say that all the body which is executing the uniform motion and its projection behaves like a simple harmonic motion? which satisfied f is equal to minus k x raised to 1, then it is said to be as its projection is behaves like a simple harmonic motion it is. So what we should do here, we have to prove which, as we say, it is f is equal to minus k x raised to 1, then only particle executes the simple harmonic motion. That means if its projection on diameter, means this is a projection on diameter, acts like a simple harmonic motion it is, and it is exhibiting to and fro motion. How? Let us go ahead with this, right? So we have to prove f is equal to minus kx. We will discuss on the next here. Before going to that, it's a projection. See, so this projection on a diameter. So is this diameter of the circle? Yes, this is diameter of not. So I am taking this is the diameter here. So projection on a diameter, right, on this diameter y-axis, on this diameter x-axis. So look at this theta. How we are going to do here? We know as x is equal to a sine omega t. So this is what equation of a particle executing the simple harmonic motion. See, where x is equal to 0 to x is equal to a, it is moving to and fro motion. So this is the equation, we got it, that is of a sine omega t here. So this is the what? Equation of a particle on, simple harmonic equation of particle executing the to and fro motion, right? So theta is there here. Theta is a frame because the particle is moving from t is equal to 0 to t is equal to t here, and it's a projection on the diameter where it is executing the circular motion. So any diameter, either you can take x, either you can take y. So it is taking a projection on here. So right, so this is taking a projection which is making an angle theta here. Let a be the radius of a particle executing a uniform circular motion, and it's a projection here, right? So look at here, this is the theta, this is the base. So what are you getting here? A cos omega t. So that is of x. On x it is, correct? So whichever it is, this is a base. Angle is there here. This is the base. This is the opposite. So what are you getting here? A sine omega t. So this is parallel here. I can write it ax is equal to a sine omega t. Oh no, not omega t. So we have taken angle theta now here. So let us go ahead with the theta only. Angle is theta we have taken because it is an angular displacement where it is executing the uniform circular motion here. So a sine theta, a cos theta, because this is a base, this is the opposite part. So simple way. So how it is? It is in the form like this, right? So this is the angle here. So this will be the base. Base is there now here. This is the base, angle base. This is opposite. So sine theta here, this is cos theta. So here diameter is the same format I have drawn here. So this is the diameter, this is the projection. So this is also projection we did. So you should not get confused. I'll draw it as a dotted line only. So this is parallel, so I can write it here. This is also sine theta, right? So x is equal to a sine theta here, where theta is equal to what? Omega t. Where theta is equal to what here? Omega t. So projection of a particle executing the uniform circular motion on a diameter a sine theta is there here, where theta is equal to omega t. So a sine omega t. So x is equal to a sine omega t. So what is the equation of a particle executing the simple harmonic motion? Just now I have written x is equal to a sine omega t. Is this same as this? When we are discussing the particle executing the simple harmonic motion, it's a projection on the diameter. Any diameter, you can take a y axis or x is diameter of this circle. So it will be fixed, no, as the radius of the circle is going to be fixed any point on the circumference. These are the basic thing, right? Or wherever you can take, that will be remains as a sine omega t, means it's a projection where the body executing the uniform circular motion behaves the periodic motion. Obviously it is purely periodic motion. Then how we are going to study with this phasor diagram? Phasor diagram means where we can see the phase of the particle under the where it is executing the uniform circular motion. So that's why it is called as a phasor diagram. So that's why it is called as a phasor diagram. So it is proved it's a projection which behaves like a to and fro motion. As in an oscillatory motion, which particle executes the to and fro motions act as a simple harmonic motion. Means any one of that one will act as a simple harmonic motion where the particle experiences the force trying to move towards the mean position. So in this, how it is act like a to and fro motion, let us move ahead here. So this part with the equation we have proved, it's a projection. It's going to be act as a equation of simple harmonic motion here. By keeping this diagram only, we'll go ahead with the understanding it's a projection here. So let us go ahead with a circular form here, right? So we'll take it as a x is equal to 0 in this part, where t is equal to 0 here, right? As x is nothing but the displacement here, and d. So when you go ahead with this part with a simple harmonic motion, so let us go ahead with a simple harmonic motion. X is equal to 0 here, as a t is equal to 0. When it is moving towards the extreme position, x is equal to positive, right? And it is moving towards the negative extreme position, minus here x, right? So when the particle is moving from t is equal to 0 to t is equal to t here, so draw the projection here. I'll call it as this is a p1, means projection first. So again when it is moved towards the t is equal to next t, so this projection, if you draw it a projection here, so you should not get confused. We'll take only one projection on any of the diameter. So I'm taking this part here. So projection here, I will call it as this is P2. So how it is moving towards the extreme position. So I'll call it as it is a A. I'll call it as this part as a minus A. Same this format I have drawn here. So particle is t is equal to 0 to, it is moving towards t is equal to t it is. And the next it is moving towards the t is equal to, say t1 is there, t is equal to t2. Just to identify how it is reached, right? This part it is. So t1 and t2. Again once it is reached here, it will comes towards the this position. Its next moment it starts here. So it is coming this point. So draw the projection here. I'll call this is a P3. Now after this is a P1. So P2 here. So next it is coming towards the mean position. So towards the mean position, that is a P3. So I'll call it as this is nothing but the P3. So this part means it's going to be reduces its speed or the velocity, where velocity is a maximum at the mean position, velocity is 0 at the extreme position. That we know already. In the previous class we have already discussed. So again it is moving towards this point. So draw the projection here. So I will call it as P4. So reach to the mean position here. Reach to the mean position. So let us continue to be move to the next. It does not stop here only. It will move, no, as in a simple harmonic motion also, or a oscillatory motion of the particle also. The particle executing the circular motion also. So draw the projection here. I'll call it as this is a lattice. So let us moving in this. We'll call it as this is a P5 projection 5 here. Again it will continues to move in this direction. So draw the projection. So P6 it is. What it indicates? So look at here. This is coming towards the negative extreme position of a particle. So again it is coming P5. Again it is coming P6 it is. So it is moving towards the extreme and negative extreme position it is. Once it is coming negative extreme position, it will not stick here. It will move towards the moving towards the mean position. Moving towards the mean position. Same things it is happening in the body executing the simple harmonic motion or the to and fro motion it is. So it is coming here and it will try to come to this position. So look at here. This is the projection I'm going to draw here. P7 and reach to this point. So what is the projection here? P8. So this is the P8 moving towards the mean position. Same it is happening. Look at it. P1 first positive extreme position. P1, P2, P3 here, right? And P4 and coming here P5, P6, P7, P8. So look at here. P1, right? And P2. Which direction it is? P1 and P2 positive direction. And it is moving towards the extreme position it is. And again, it is coming P3 and P4. So P3 and P4. I am not writing vector here. Direction I am writing. In which direction it is moving. So it is moving towards the mean position. X is equal to 0. Right? So it is in this extreme position. This is on mean position. Again. So look at here. P, what is that? P5, P6. Correct, no? So P5 it is. This is for this. P8, P7. I'll write it here down so that I will not get confused. So P5 and P6. In which part it is? P5 and P6. Moving negative extreme direction it is. Negative extreme direction or the negative extreme path here. So it is moving negative. Again, P7 and P8. P7 and P8. Where it is moving towards the which direction? X is equal to 0. So once you draw the same path here, X is equal to negative here, X is equal to 0 or X is equal to positive here, right? Next, here it is moving, that is P1 and P2. Here it is moving P3 and P4, right? Again, next it is moving P5, P6, P7, P8. So it is exhibiting the simple harmonic motion. See how it is. It is moving, coming and trying to meet towards the mean position only. Force is experienced by the particle here. It will try to move towards the mean position and it will not stick here only. It will come towards the negative extreme position. Again, it will try to move towards the mean position only. What is the concept here? The body or the particle executing the simple harmonic motion try to move towards the mean position only. So here the body experiences or the particle experiences a simple harmonic motion when it is uniform circular motion. We'll never say it is a simple harmonic motion, but its projection will act like a simple harmonic motion. That is proved with the equation given x is equal to a sine omega t, where theta is a omega t. Omega t means what here? That is of angular displacement. How it is? With the base part it is a cos theta, with the opposite part a sin theta, where we have taken the projection on the diameter here. So a sin theta here, where theta is equal to omega t. So this is proved with the, it will act like a simple harmonic motion here, and this part is over. F is equal to minus kx, either we have to prove, or acceleration minus omega square x, F is equal to minus kx raised to 1, or the particle a sin omega t. This is proved, and we have to go ahead with the ax is equal to a sin omega t plus phi, general equation. So either this has to prove as this has to prove here. So let us go ahead with understanding one smallest problem, so that it will be easy to understand. So projections are taken as a x here. So let us go ahead with taking the one problem. If the particle experiences the uniform circular motion here, uniform circular motion of a time period is given as a 4 second and amplitude as a 2 centimeter here. So what is the equation of a particle executing in the simple harmonic motion? With the phasor diagram we will prove it now. Right, this is a x here, where t is equal to 0 to, it is moving certain distance, say about t it is. So this will act as a theta here. No. So this will act as a theta. Y means moving from t is equal to 0 to t is equal to t. So always you should remember, it will start from t is equal to 0 to at any direction it is. We will solve the some other problem so that you will understand how we have to take it as the help of a phasor diagram to solve the problems related to simple harmonic motion here, right? So where omega is equal to what it is, sorry, theta is equal to omega t. So draw the projection here, right? So draw the projection. We have a sin theta here, where x is equal to, this is not needed, no need to write it here. So x is equal to a sin omega t here, right? A is given, what is of 2 it is. So sin omega t is there, where omega we have a relation that is of what, 2 pi by t. So 2 pi is there, t is a 4, that is of pi by 2. So that is of pi by 2 here, a sin pi by 2 t. So this is the equation of a particle where it is executing simple harmonic motion by solving the phasor diagram here. So let us go ahead with the one more part. One more part means in a clockwise direction. If this theta is a given, and we have to prove with the phase it is, that means x is equal to a sin omega t plus phi. This is a general equation we have already known. So you need to understand here, a sin omega t means what, particle is moving from mean to extreme position, and we know when particle is there on extreme position to mean position, what is that, x is equal to a cos omega t, and general form of it was a sin omega t plus phi and a cos omega t plus phi. So this is the general equation. What is the phi here? Phi is a initial phase. What is the phi? Is initial phase. So now it will comes into the action, the utilization of a phi in the phase diagram here. So that is very important here. Now let us consider initial phase. Body is executing the uniform motion and trying to move towards the t is equal to 0 to t here at an angle phi. So look at here, at t is equal to 0, this phi what will be there? It will not shape any angle at t is equal to 0, because it is there at this position, there is no any other angle on it. So if you t is equal to 0 means phi is equal to 0. So that's why you are getting x is equal to a sine omega t. When you play with the general equation also, at t is equal to 0, particle does not swipe any angle here, which shows the phi. Particle does not shows any angle which shows the phi here. So once we'll go ahead with the particle is moving from t is equal to 0, not at the mean position. At that time, what will be the case? So let us go ahead here. Until then, we have studied at a t is equal to 0, particle is moving here. But particle is at the extreme position here. Here t is equal to 0. So if you go ahead with the drawing this part, from here the particle is start moving towards the t is equal to t. So look at here. This is very important. Now until then we have studied t is equal to 0 at the mean position. So how means particle is moving from x is equal to 0 to extreme position x is equal to a. In some other cases we have studied here, particle already at this position and it is moving, or particle may be already it is a by 2. At this point t is equal to 0 when it starts the simple harmonic motion or the position. So are you getting? So once check here, particle is there at the negative position, particle is at the mean position, particle is at the positive position. If it is moving from a mean position to extreme position, we have the equation that is of a sine omega t. When particle is moving from extreme to mean, we have a x is equal to a cos omega t, right? A cos omega t, moving from extreme position to the mean position, right? Similarly, when it is moving from extreme position to mean position, at this point t is equal to 0. When it is moving from mean position to extreme position, at that time t is equal to 0 here. This you need to understand properly. When the particles begins to show the simple harmonic motion or the motion, at that time period is 0. Whether it may be in the mean position, whether it may be in the extreme position given in the problem, or it is said to be in that. When it is started at the extreme position, means equation is given here, at that point t is equal to 0. Similarly, in this circular form of the particle, its projection we are studying right now. So it is starting from t is equal to 0, then we have already a sine omega t. It is proved. That means at t is equal to 0, particle does not sweep any angle. So phi will be 0. Phi will be 0. Then it is said to be as a sine omega t here. Now, the particle is moving from here. To reach this point, particle has to move from here only. That means x is equal to 0. It is a circular motion. Body executing the periodic form. Means it has to start from where it is there. That point we will say it as it is a x is equal to 0. So from here to here it has to move. Means we have to measure from always at this point, beginning point. As in case here, amplitude must be measured, displacement must be measured always from the mean position. Wherever it is, always x should be measured from mean position. Same case it is moving anywhere in this form, but it is started from here like this. So you have to consider this. From this point only it is started beginning, right? So after this when it reached to this point, no, here it starts begin to show the uniform motion here to reach this point t. So this will becomes what here? Angle sweep. I mean angular displacement omega t here. What about this? This is nothing but the phi. Why phi? It is initial phase where it is started the motion. So this is the initial phase. So up to this you have understood. Now give the projection about this. So projection is made for where it started the journey. So this point it is. Projection this. Look at this. Projection is this format. So what is this? X is equal to a sine, not only theta here, because total journey from here to here it is. From here to here. I said no, it is not from only here to here. Body is to reach this point, it has to travel this now. So this is the initial point or the initial phase where we can see the particle executed. In this case also, wherever you can take, particle is there here, particle is there here, x always measured from mean distance. X always measured from mean distance means displacement measured always from mean distance. Similarly here also. So initial phase where it started the journey, that is theta plus phi it is, where theta is what here? Omega t. So x is equal to a sine theta plus phi it is. So total it is. So this part, no, this is the complete projection it is. From t is equal to 0 to t. To t is equal to 0, it is not at the mean position or the original position. It is shifted. Shifted from mean position to the certain point where it started the journey. That time t is equal to 0. This condition and this condition. This condition, phi will be sweeps no angle. That's why you are getting a sine omega t. And here you are getting a sine omega t plus phi. Phi is the initial phase where it is started from t is equal to 0, but measure from this point, mean position. So this concept you have to understand. In the next class, we'll solve based on this concept some numerical problems.